Hi, this session gives a quick overview of all the things that you need to know for paper 1 and a few useful tips as well and what to expect. We know that we're likely to get a long answer question, which is the one you write in kind of an essay format. Make sure that you talk about all of the bullet points that they give you in the question. Also, make sure that you give positives and negatives. Look at both sides. Why might some people think something's good? Why might people think it's bad? Look at both sides to get those top marks. And every time you make a point, develop it. Don't just make your point and say something. Give an example. Give your reasons why. Give what that could result in, how that could make people feel. Develop it to get in the top marking. We know that these questions can often be the kind of ethical, legal, cultural areas. So ethical is all about whether it's the right or the wrong thing to do. Environment is obviously, does it help or hurt the natural world? And then cultural is about changes to communities, how people live, how it affects people's kind of lives and how they might have to adapt and change. And then legal, there's some laws that we need to know for the exam. In terms of ethical, it could include things like, you could talk about things like whether people might think it's right or wrong and why they might think that. There's often issues of replacing people with machines whenever things like AI or technology is involved, and that can obviously have a negative impact if people lose their jobs, skills are lost over time, and it can change how people feel. People don't necessarily want to deal with a machine as a customer, they might prefer a person and that human touch. Improved efficiency and accuracy is a benefit, so we know that machines don't make mistakes, they don't get tired. Social pressure, we can look at things like cyberbullying, when people are pressured to get new devices or have the most up-to-date technology. We've got digital divide, so the difference between people who do have access to technology and those who don't, often due to cost, but it might be due to availability of where they live in the world. Loss of jobs, I've already mentioned. Privacy, so privacy is an ethical issue. Do people want to be, for example, spied on by CCTV or monitored to check they're working from home correctly? The environment, we can talk about things like pollution. When technology is made, it's made in factories, that obviously has a pollution aspect. We've got the use of energy, both to make the devices and when devices are actually used. The use of raw materials to make them. E-waste, so e-waste being when technology is no longer needed and it is dumped in landfill and causes pollution. Then we've got the cultural issues, so some of these will cross over into ethical, like the loss of skills. When jobs are given over to technology, we gradually as society lose those skills. It gives changes to the way that people in communities live and work, and people might not be happy with that. But it can also create new jobs and develop new skills. So, for example, we develop more programmers and people that can fix the technology when it goes wrong. And again, the digital divide can be mentioned in there. And then in terms of legal, there's 3 laws we have to know about. We have to know about the Data Protection Act, which is all about keeping data safe and secure, up to date and accurate, only using it in the way that you've said you're going to use it, all of those things. And you can always give examples of that as well. So you might keep it safe and secure by using encryption, by making sure that only staff that need access to it have it, those kind of things. Then there's the Computer Misuse Act. That's the law that prevents hacking and the creation of viruses. And then we've got the Copyright Designs and Patents Act. Always call it its full name, never shorten it to copyright, they won't give you the mark. And copyright is protecting people's work and their creations. And then we've also got the kind of legal aspect of who is to blame if something goes wrong. So if technology goes wrong and then someone gets hurt, is it the programmer that's to blame? Is it the person that was maintaining it? There's all sorts of issues. And the final legal issue that can come up is licensing. So we've got open source and proprietary software. When you create software, you can release it under one of those licenses. Open source is where you're releasing it so that other people can have the source code, they can edit it, they can make changes, they can improve it, they can make it suit their needs. And there's lots of benefits of that. People can develop it and make it better. The downside is that you as the programmer, you kind of lose control over your program because other people are making changes and you can't charge money for it. Then you've got proprietary, which is where you release it and you sell it and you don't give people the source code. They just get the actual program and executable file to run. The benefits to you is that you can keep control. People aren't going to be able to take, copy, or use your program in any way that you haven't intended it to. The downsides are you have to make sure that it's really well developed without bugs. You're going to have people paying, so they want that to be to a high standard. Then we're on to the CPU. So the CPU we know stands for Central Processing Unit. They could ask you that. And it runs this fetch, decode, execute cycle. And where it is fetching data from is the RAM. So it fetches data from the RAM and it then takes it back into the CPU, decodes it, and then executes it, or runs whatever that instruction is. The parts of the CPU that we have to know about, we've got the ALU, the arithmetic logic unit, and that does all of the maths and the logic calculations. Clue is in the name. And inside the ALU is our first register, and we have to know about the registers. So we've got the accumulator, and the accumulator holds the result of any calculations that have taken place. So then we've got the register section with the MAR and the MDR. The MAR, the memory address register, again, clue is in the name, holds the RAM address for the data that's being processed. Whatever instructional data is being processed, the MAR holds the RAM address for that piece of data. And then the MDR holds the data that's about to be processed. So whatever data is being processed or about to be processed is held in the MDR. That's the actual piece of data. The control unit controls the flow of data in the CPU, and it contains another register, the program counter. And the program counter holds the address of the next instruction that's going to be fetched, the next instruction in the RAM. And that's how we keep track of where we are in that fetch, decode, execute cycle. So on every cycle, the program counter increases by 1. And then we've also got the cache, which is very close to the CPU, and it holds frequently used or recently used instructions, and that's so that they can be fetched more quickly than from the RAM. We've got primary storage that we have to know about, also sometimes called memory, and we've got the RAM and the ROM as part of that. RAM is volatile. It loses its data as soon as you turn off your power to your computer, and it holds the data and instructions for the programs that are currently running. The ROM is non-volatile. It does not lose its instructions after the power is turned off, and it holds the boot up sequence and the BIOS. We don't want that to be volatile because it's important that our computer is able to turn on each time. The secondary storage, we've got 3 types: optical, magnetic, and solid state. Optical, we're going to look at first. It includes DVDs and CDs. It's cheap. They have a low capacity. They're physically quite small, so they can be portable, but they're not very robust, so they're not the best option for portability. But great if you just need something cheap for a few small files. Magnetic is your hard disk drive. It's a high capacity, holds lots of data, cheaper than solid state. It's got moving parts that makes it less robust than solid state. But the good thing is that if you're using a computer that doesn't need to move around, it doesn't matter that it's not robust. Solid state can be the solid state drive, SD cards, a USB memory stick. It's got a high capacity. It is more expensive than magnetic storage. It's robust. It's got no moving parts, so it's great for portability in terms of like a USB memory stick because you can carry it around. It's not going to get broken. And it's got a fast read-write speed, which is also quite useful. Then we've got virtual memory, used when the RAM is full. Data is moved from the RAM to the secondary storage. So if your RAM gets full, the data is moved from the RAM to the secondary storage, so your hard disk drive or your solid state drive, and that will make space in the RAM for new instructions and data. And then the data that's been moved is moved back to the RAM when it's needed. In terms of binary, we have to know the binary headings. We start with the ones column, they double as they go up. This example here is an 8-bit binary number. It's got 8 column headings, and that's also called a byte. Any columns that have got a 1 in them, we know that we add those column headings together, and that gives us the denary number. Binary shift, we have a number, an 8-bit number like this, and we will be told which way to shift it. So if we're shifting it like this one, 2 bits to the left, then every bit on our 8-bit number moves 2 places to the left. So this 0 would move 2 places along to the left like that. And the other numbers would all move along 2 places to the left. When we get to the end, we lose these, they are lost, and we fill in any gaps like these with zeros. Moving to the left, doubles, moving to the right, halves. And then we've got binary addition. I would always suggest that when you do binary addition, before you do it, at the side of your paper, write 1, 2 and 3 and put what they are in binary. 1 is just 1, 2 is 1, 0 and 3 is 1, 1. That will make it almost impossible for you to go wrong. So in this one here, we're going to first of all add together the 1 and the 0, which is 1. And so 1 and 0 is 1, and we just pop that in there. Then we're going to add together this 1 and 1. 1 plus 1 is what we know as 2, but we show that as 1, 0. So we put in the 0 and we carry the 1. Then in this column, we've got the 1 that we carried plus the other 2 up the top. So 1 plus 1 plus 1 is what we know as 3, but 3 is shown as 1, 1. So we put in the 1 and we carry the 1, which I'm just going to then pop up there. And that gives us our answer. And that's how we show binary addition. You could also get asked about this. This is an overflow error. So it's where two binary numbers have been added together, but the answer does not fit in 8 bits. So that is an overflow error. That's a term that you need to know. Hexadecimal, we've got 16 possible options, the numbers 0 up to 9. And then once we get into double digits, they are represented by letters. So A, B, C, D, E, and F. They're used by programmers, hexadecimal numbers are, to represent large numbers with fewer digits. And just a quick reminder, we can work out a number by splitting the binary number in half, putting in our column headings, and we treat each number separately. That's the point of the line down the middle. On this side, we've got 12. On that side, which is C because of the letters, on that side, we've got 9, and that would just be 9. So that binary number in hexadecimal would be 9C. When we've got 2C like this, we split it down the middle and we do the same process in reverse. So we work out what we've got on each side. We know that C is 12 and we know that 2 is just 2. We showed 12 as a binary number, and then we're also going to show 2 as a binary number. We've then got all of the digits we need. We just need to put them under the original headings. So I repeat the numbers, but under the original headings. And when I add up any of the columns with 1s in them, we get 44. Characters, we have to know the term character sets. That's all of the characters that a computer system can represent. And each character is represented by a binary number. The character sets that we need to know about are ASCII, which represents 256 characters with 8 bits per character. There are less character options, but less storage per character. So ASCII, a benefit is that it doesn't have take up a lot of storage per character, or as much compared to Unicode. Then we've got Unicode, which uses at least 16 bits per character. So you've got more character options, but each character is going to take up more storage space. Images, we know that images are made up of pixels, those little squares of colour. Each pixel is represented by a binary number. Each colour in an image has a different binary number. And so we've got here an image where there is just 1 bit, so a colour depth of 1 bit, where every pixel has 1 binary number. So that gives us 2 options, 0 or 1. The number of bits indicates how many colours are available for each pixel. We've got resolution, which is another term we need to know, how many pixels per inch. The higher resolution, the higher quality and file size. Metadata is that term data about data. And so it's things that are stored with your image. So like the date it was taken, the time it was taken, the GPS location, the dimensions, the height and width, and the file format. And there we've just got a reminder on colour depth of how many colours can be represented with different numbers of different colour depths. Sound we know is a wave, and we've got sampling, which is where the height of the wave, the amplitude, is measured at set intervals. A higher sample rate means more samples, so a higher quality sound, but a bigger file size. So when we sample at more points, more frequently, we're going to have more data to record, so bigger file size, but the quality will be better. We've then got bit depth, which is a bit like colour depth, but in this case, it's to do with how many bits are used to record each sample. If you use more bits, you're going to have a higher quality file or higher quality sound, but it's going to be a bigger file. And then duration is just how many seconds long the sound is. And that will be in seconds usually, and it doesn't affect quality, but it does affect file size. Having a bigger or a longer sound isn't going to change the quality, but it is going to make your file size bigger. If you're asked to calculate file size, you will be given some pieces of data. So for example, for sound, you'll be given the sample rate, the bit depth, and the duration. The trick is just to multiply them all together, like the example on the board. Once you've multiplied them together, you get your answer. So anything to do with file size, if it's to do with sound files, text files, image files, calculate the things that calculate the answer by timesing the things that you've been given together. Compression makes the file size smaller. This makes it faster to upload or download, and it can also make it take up less storage space. We've got lossy compression, which is where data is permanently removed. It's suitable for images and sounds, as some quality is lost, but usually not very noticeable, and it makes the files permanently smaller. Lossless compression is where an algorithm is used to make files temporarily smaller. They do not lose any quality, but the file size can't be reduced as much as it can with lossy, and it's only temporary. So it's best for programs, text documents where you wouldn't want to lose important information because they wouldn't make any sense, but isn't going to reduce it as much. Network hardware. We know that networks just connect devices together so they can share resources like files and printers. We've got different pieces of hardware we have to know. So the router, which joins networks together. So it joins your home network to the WAN of the internet, for example. And routers send data between networks. That's one of the jobs that they do. A switch connects devices together. So whereas a router connects networks, a switch connects devices together to form a network, and it directs the data between devices. A wireless access point allows devices to connect to a network without wires, and it's usually built into a router. A NIC, network interface card, or network interface controller, it can be called either, allows devices to actually connect to a network. Transmission media just means the way the data is carried, so whether it is carried by signals through cables or through wireless. Topology, the physical arrangement of the connections in a network. So we've got a star topology on the left, where in the middle is a switch, and all of the nodes or devices around the edge are connected to that central switch. Positives are that if one node or device goes down, it's not going to affect the others, but the downside is you've got a central point of failure. If your switch breaks, your network is down. Then with a mesh topology, you can either have a partial mesh like the picture in the middle, or a full mesh where every single device is connected to every single other device. And so the benefits of a mesh topology are that there's multiple paths the data can take. So if a device fails, it's not going to affect the others because the data can go a different way. And there's no central point of failure. There's no switch in the middle that's going to fail and make it all stop working. The downsides of a mesh is that they are expensive and more complex to set up. Methods of connection, we need to know wired, which is Ethernet cables, and we need to know wireless, which is Wi-Fi or Bluetooth. They could ask you, give 2 examples of wireless networks, and you would say Wi-Fi and Bluetooth. Wired networks, you've got cables limiting your location, but you've got a faster connection. You've got less interference, you can cover a longer distance. Whereas with Wi-Fi, you've got more freedom to move around. You can use that device anywhere in the range, no cables to trip over, and you do have the downside of interference from barriers like walls and a shorter distance that you would be able to have your device. In terms of the internet, we have to know that the internet it's one big WAN. It's a worldwide collection of computer networks. We've got the term hosting, which is the storing of files and data on a web server, and the web server is referred to as the host. The term DNS, domain name server or domain name service, every website has an IP address, but these are hard for humans to remember, so we use URLs, those kind of wordy addresses like www. blah, blah, blah. And the DNS matches the URL to its IP address, and then it sends the user request on to that address. The cloud is remote storage accessed over the internet, and it can be used either for backups or for your general storage of your data. And it means that files can be accessed from any device that has the internet. File access can be shared with other people, so that's useful to work together on things. And cloud services will make backups for you, so they will do the backups and the security for you so that you don't have to. You can only access your files if you have internet access, and you've got no guarantee that the cloud services are backing them up correctly or keeping your data secure, so that's the downsides. MAC addresses and IP addresses. We've got MAC addresses are what's assigned to the device by the manufacturer when it's made so that it can connect to a network. They cannot be changed, they're unique, and they look like that. IP addresses are used when sending data between networks. They're assigned before a device can access the network. And we've got two types, IPv4, which uses 32 bits, and IPv6, which uses 128 bits. IPv6 was created to allow there to be more unique IP addresses. And then IPv4 is denary numbers, whereas IPv6 is hexadecimal numbers. Standards are just an agreed way of doing things, and they make it easier for people to build programs and software that work on different systems or by different manufacturers. And that's all you need to know about standards. In terms of threat prevention methods, we've got anti-malware software, which detects and removes viruses. We've got firewalls. They monitor the traffic that goes in and out of a network, the data traffic, and they identify threats or stop data leaving when it shouldn't or coming in when it shouldn't. User access levels. They give people access to the files and programs that they need. They don't let them have access to things they don't need, and it helps prevent accidental damage. So it might be that you stop people having the ability to change certain settings who you wouldn't want to have that. And it can be to do with like levels of seniority in a company, for example. Encryption scrambles data using a key so that if it is intercepted, it cannot be read. Penetration testing is where we deliberately try and break into a computer system to identify what weak spots need fixing. And then physical security is things like locked doors, passcodes on doors, etc. Threats, we've got malware, which is software intended to cause harm. Brute force attack, which is repeated attempts to guess a password. Data interception, data being stolen while it's sent. Phishing, when emails try and trick you into entering personal data. SQL injection, where people enter harmful SQL code into an input box on a website. And social engineering, when people are manipulated into giving you access to a computer system. Malware is obviously prevented by anti-malware software. Brute force attack can be prevented by having a limit to how many times you can guess a password before it locks you out. Obviously having a strong password, two-factor authentication. Data interception is prevented by encryption. Phishing is mostly about kind of training, if you're training your members of staff not to fall for that sort of thing. SQL injection is prevented by validation on the input boxes. And then social engineering can be prevented by staff training and having certain rules about how things are dealt with. Network protocols, everyone's least favourite topic, is rules. The protocols are rules about how data should move on a network. And we've got some that we have to know. So we've got TCP/IP, HTTP, HTTPS, FTP, POP, IMAP, and SMTP. The way to remember it, HTTP we all recognise is to do with websites and the internet. HTTPS is the more secure version, the encrypted version of that, used for when you're paying, like sending over your bank details. FTP, if you know what those letters stand for, file transfer protocol, is obviously anything to do with files and opening them, moving them on a network. Then we've got POP and IMAP. They are both to do with receiving emails. The POP protocol, Post Office Protocol, is where once you receive an email, it's no longer stored on the server, you have the original. Whereas IMAP is where you are just seeing a copy of the email, the original is stored on the server. And then SMTP is the one that's to do with sending emails. The way I remember it, it's the only protocol that starts with the letter S, so therefore it's the only one that's to do with sending emails. And then TCP/IP right at the top is all to do with how data is sent on the internet. Similar protocols are grouped in layers. So you might see the term layers in the exam paper. And the purpose of layers is to group together similar protocols, and also so that each layer can work independently. You can make changes to one layer without it affecting the rest. In terms of software, we have to know about operating software, the software that manages and controls the computer, and utility software, which helps keep it running smoothly. They're the two bits of software we have to know about. In terms of utility software, we've got defragmentation, compression, and encryption. Just jumping back to those slightly. So defragmentation is when we have a magnetic hard disk drive and our data over time has become fragmented. It's scattered over the hard disk drive. It's ending up being very slow for it to read and write to, because it's having to move around so much to find the data. Defragmentation moves all of the fragments for each file. So file 1, all the fragments would be moved together, and so on, and all of the free space together. So it improves or speeds up read-write time. Compression, we know, is making file sizes smaller. We talked about that a minute ago. And encryption is scrambling data using a key so that if it's intercepted, it cannot be understood. It can only be decrypted by the intended recipient, the person that you meant to send it to. With operating systems, that's the software, as we said, that manages and controls the computer. We've got file management as a role of the operating system, a job that it does. Anything to do with your files. So when you go to delete a file, when you go to name or edit the name of a file, all of those things are done by file management. User account management obviously manages your user account, so giving people the settings that you want them to have, creating and deleting accounts. Providing a platform for apps allows you to download other apps onto your operating system. Memory management or multitasking is what manages your memory. And so it is going to allow your computer to do multiple things at a time. It manages your virtual memory. Managing peripherals or managing hardware, so the devices that you plug in, like if you plug in a new webcam, it will download a driver so that that device can communicate with the hardware of your computer.